Hello, everyone, and thanks for joining our session on next-gen Kubernetes threat handling. My name is Michele Dodic. I'm based in Munich, Germany. I'm a site reliability engineer and solution architect at Accenture, also an AI Ops and Chaos engineering SME and expert, currently leading our site reliability engineering practice in Germany, Switzerland, and Austria. In the past years, I've been working on projects aimed to help our customers from different industries to enable observability and AI ops into their systems. Francesco, over to you.
Thank you so much, Michele. I'm Francesco Sbaraglia. I'm based in Australia, in Sydney. I have 20 plus year experience in SRE, DevSecOps, and K8s engineering, currently leading the Accenture SRE and observability practice in Australia and New Zealand. I've been working in multiple enterprises, startup and government. If you already watched other talks, I'm expert about security K8s engineering. Let's go next with the talk of today. So we have the agenda. So first of all, we will start with the motivation. Michele will intro about eBPF, what is and how we can use it. We will have a look on the proactive threat hunting. We will have a live demo for sure. And then we will go through in everything that we discovered today, and we have a conclusion and takeaway. But let's start now with the motivation. In the world of cloud native, we can identify various challenges that organization faces. First of all, we have runtime security. Critical to detect and respond to threats that they happen, risk like container escape, privilege escalation, and execution of unauthorized code. Those are real-time issues that we need to be more proactive in detection. Then we have anomaly detection. Today's threats don't always follow known patterns. Attacker uses sophisticated technique and exhibiting abnormal behaviors. Whatever it's identifying misconfiguration or blocking a security zombie, leftover resources that remain exposed or running in our system, we don't know when they will stop or when they will become active. It's essential to catch this issue before they escalate. Last but not least, for sure, we have monitoring of their internal threats. External attackers aren't the only concern, but typically we have malware and ransomware that maybe they run already inside our Kubernetes pod and in this multi-cloud environment, and we don't know when they will get activated. And the fact is that how much we can deploy into this environment and the whole frequency that we have, we will always have the risk of having classical normal microservices, but with embedded inside security threat. Therefore, it's crucial to flag unusual activities, the one that usually maybe they have a different behavior, and then to track this behavior and have a look on what's happening under the hood. These kind of challenges highlight the need for more proactive solutions. And that's where approaches like Kubernetes threat hunting, use GenAI and eBPF come in. The slide illustrates a classical multi-attack framework. It's a comprehensive matrix that maps various techniques across different stages of an attack lifecycle, from initial access to the impact. You can see how complex and multifaceted the threat landscape is for a cloud-native environment. Attackers have a variety of methods to infiltrate and exploit Kubernetes environment. By understanding these techniques, we can better prepare defenses, build a proactive threat hunting strategy. In the live demo, we'll have a look on one of them. And actually, that's really interesting because we will do a live one. So you will see how we typically react based on the different attack that we will the classical attacking surface on a Kubernetes cluster. Of course, we have to start on the fact that when we talk about cloud native, most of the time we also refer to Kubernetes. And actually, there is more than 80% of the whole cloud native architecture worldwide. We are, of course, based on Kubernetes. If you see in this box, first of all, we have a master node. So we have a lot of different components here. etcd, the control plane. So imagine how much this can be critical if we are exposing. Then we have worker nodes, because of course, in cluster, we have the classical node. They will run our services or our pods or our maybe processes. We have Kubernetes that can be accessed via API. Also work pod where our app will run. at different level, different vulnerabilities of attacking surfaces, one can be expected different cyber attacks. Run another instance of a kubelet on the same node. So imagine how critical it is. Privileged pod that can run and scan the pod and inject malicious causes everywhere. This webhook, of course, we talk about that we have connection outside. We have maybe other API that this webhook can call outside, maybe can bring other files inside and other threads. We can get a token from outside and read these other tokens and gain maybe or even security access. Based on this, we can also derive that from security vulnerabilities, I could misconfigure my container, or we could have a malicious container already running. This will try to escape and get them some other information everywhere else. And we will have a look actually also on this part on the live demo. But what can also happen is an international cluster misconfiguration. I will leave the word to Michele because he will introduce about eBPF.
Thank you, Francesco. Before jumping into proactive threat detection techniques, let's first take a look at eBPF. Those who worked extensively with Kubernetes environments know how hard it is to troubleshoot issues inside containerized applications, or inside containers in general. It is often seen as a black box approach, and this is the reason why we need eBPF. Let's do first a precursory check. eBPF stands for Extended Berkeley Packet Filter, and it can run sandbox programs in a privileged context. So basically, eBPF extends the OS kernel without changing the kernel source, without requiring a reboot, and without causing any crashes. Let's now see how eBPF actually works. Let's start from the user space, where we attached our application, microservices, networking components, and various other processes. Then we have the kernel space, and at this current point in time, entirely decoupled from the application. However, the application process will at some point trigger a system call. For instance, execv, as most of execv is used to execute the new program within the current process. And the system call will then create an event, which is then calling the eBPF program that we have injected. This way, every time the process executes something on the kernel side, it will run the eBPF program. And this is very helpful because when an incident in production occurs, we can track and understand all system calls inside the kernel. And this is why we say that eBPF programs are event-driven, and this is how we increase awareness from the kernel side. Overall, eBPF tools have the ability to instrument the system without requiring any prior configuration changes. And in this way, we strengthen the coupling and context awareness between the kernel and our app sitting in the user space, and the kernel becomes a sort of big brother as it sees everything. So this is why we say that we instrument, so with eBPF, we'll instrument the kernel on a more cloud-native level. Okay, so we learned about the basics of eBPF and its benefits, but what is actually an eBPF frontend and what does it look like? So the question we want to ask ourselves now, from a technical perspective, how do we load our eBPF program into the kernel? Let's, for example, take a look at this Python code that compiles our eBPF program. First thing we need is to load the eBPF library, which we need to move the program inside the kernel. I then have my eBPF Hello World program, which is loaded and attached to the kernel via our execute system call. Remember, the system call will invoke the hello function, meaning every time a new program runs in this virtual machine, my hello eBPF program will be triggered from inside the kernel. Okay, before we jump into proactive threat hunting approaches, I suggest we first take a look at the more classic, traditional approach for threat hunting, which used to be reactive. So let's start with a couple of these. Rule signature-based detection. This one relies on static predefined rules. And therefore, if you think about it, it misses the unknown, it misses evolving threats, making it ineffective against new attack vectors. Log and event analysis. Also manual, meaning slow and missing real-time threat detection, so it requires human-driven investigations of the logs after an attack has occurred. Let's look at the IOC analysis, indicator of compromise. Provides KPIs that indicate system vulnerability but you don't know why, since it's only a scoring. It's also retrospective, focusing rather on aftermath than on prevention. As you can see, all of these techniques are limited by reactive factors that limit scalability, are unable to detect novel or advanced threats and sophisticated attacks. They only focus on what is already known. They're mainly human-driven, and therefore often produce high rates of false positives and false negatives. So in other words, what we need is modern proactive threat hunting approaches. So let's consider this use case to crystallize this a bit better. Imagine that you are a site reliability engineer and you have deployed a containerized application. So we're talking about the Kubernetes cloud native environment. Obviously, before you deploy this to production, you want to run some tests and make sure that everything is correct and running smoothly before you deploy this. So what we do, as we have introduced earlier, we attached eBPF and observe the various events. We filter the events that are relevant for us. And then what we do, we feed these eBPF logs into our GenAI plugin, might it be I or any other one. But the idea is to set GenAI so that it can check for any security vulnerabilities inside the eBPF logs. For instance, what we have done for this use case, which Francesco will also show later, is basically we have on purpose injected etc password inside the logs, meaning that the etc password file can be accessed by a process. So it's exposed inside the code, and it is obviously a vulnerability risk. So what we do is we extract this via eBPF, we feed it into GenAI, and GenAI will recognize this. So later Francesco will show, but if you look at these kind of eBPF logs, they are huge. Going manually through these logs and checking any anomalies or any issues, it's close to impossible to do it by hand. So with GenAI, we can do this in real time. What happens is that GenAI identifies this anomaly, identifies this security vulnerability, and then it does the following things. So first of all, it sends a proactive alert to the site reliability engineer so that the engineer is aware that something is wrong. And what you can also set up very easily is you have an observability dashboard. You can also directly visualize this on your security control center, as we are calling it here. It's quite small, but I think that you can see. So if you look at the figure to the right, if you look at the control center, you can see that the SRE can then automatically check the dashboard and notice that, hey, there's a vulnerability that's been detected. The Nginx process accesses the ADC password file, which we mentioned earlier. We have here an explanation why this happened, the risks that are implicit when this happens. And then on the right-hand side here, we see the different actions that the site reliability engineer might take in order to prevent this in the future. This kind of insightful intelligence is used by the site reliability engineer to either aspect the security, but maybe also to improve the code, remove this password file, and basically improve the SML. Overall, if you think about it, this is a continuous iterated process. What are the benefits of this proactive threat hunting approach in comparison to more traditional techniques that we've seen a slide earlier? It's that we are talking about automated behavior modeling, meaning that this whole process is automated, and if there is a vulnerability, it will be detected, and that way we prevent further failure from aggregating in case this code was to be deployed to production. We are talking about real-time threat detection. Again, with the help of GenAI, we can analyze this in real time and identify a threat in real time. We obviously get a reduction in false positive in this way. And also we are talking about an adaptive threat hunting. Adaptive threat hunting, meaning that independently of the context, if we set up correctly our GenAI agent, we are able to identify any kind of issues. This EDC password was just an example.
Okay, let's have a look now on the live demo. First of all, we have a look on our nodes. So we have one master node. That's our control plane. We are running a version 1.29.9. We can have a look also on the wide, so where we can see actually also how many other nodes we have and maybe the kernel version and container runtime. Now we have a look on the Kubernetes system. So here we have running actually Cilium, as you can see. We have also Tetragon, of course, and we installed it in this namespace. So if I run now Cilium status, I see that Cilium is running correctly. We deployed using the operator, of course, and we have the different component of Cilium. Let's now have a look here. And as I mentioned before, we were actually installing using Elm, and we put the Kube proxy replacing EWALT, so that we are 100% sure actually that we are using Cilium also for our network part. So now we have a look on the list of the pods that we have. And if you can see, we deployed a microservice. Actually, in this microservice, there is one of the pod that is our testing environment. And you can recognize because maybe it's a similar naming of the other one, but at the end there is SREday. So if you see the tired one from the Dead Star. So if we have a look on one of the other pod that actually is the good one, we see that is listening on a specific port 80 and is a web server. But there is, as I said, there is one pod that actually is the one that we will use for our experimentation. So first thing that I want to do is having a look on Tetragon. So I'm running Tetragon. Actually, I'm having for the process Nmap, because I know in this experimentation I want to run a lateral movement, so I want to recognize what is in the network. I will log in inside this specific port that actually we deploy it. And in that case, I'm running the classical Nmap. The thing that I want to have is just a scanning of that IP address. In this case, the IP address is the one from control plane. And if you see, immediately when we start this Nmap, we have the eBPF events being created. So you see there are some of these events, they're already catching what we are doing actually. So as we are running the Nmap, of course, we see the binary, we see the UID, which process that we have in the parent process, and we can also even see the arguments that we are passing. Nevertheless, if you take a bit of attention, here is the container that we had, where we entered inside and we tried to execute the command, and we see as well that actually is in this case is a kernel. Another interesting part that you can see here is the fact that we have the mapping of the capability. That is really important. And now actually we go on to the having a look on the tracing policy. So I created one tracing policy. This tracing policy is monitoring actually all the file. That's why I see that I have etc password. Maybe I see that there is execution Nmap. And now if I stop actually this Nmap, what will happen is in the fact we'll catch also my stopping. So it will be a Z kill, of course, because I want to just cancel the execution, and then we can go next. So in this case, as I said, we are using the APF data, and we are bringing this APF data, EDF data into a Python script. Of course, this is just for demo purposes to show what we do. That's the eBPF data that we have. As we recognized before, there is the binary Nmap, we have the arguments, and we have also which one is the system call. In this case, we are using, except here, as also Michele was mentioning before, it's the most common one as soon as we execute them. And generally here, because we are using this SRE security assistant that we created, it's just a script. In this case, just for demo purpose, Easy is mapping based on the different actually MITRE attack stages that we saw in the previous slide, and for each of them is recognizing if this Nmap attack is fitting in one of them. And it is at the end is giving us a bit of the summary. So it's telling us, yes, nevertheless, we have this different technique that we are recognized. First of all, you are running a script. Second, you have a Unix shell. And then the third one, you have a network service discovery. And now imagine that if you run this in a CI/CD pipeline, it will be really interesting because you will catch any kind of this event happening in your microservices. And of course, with the help of generative AI, you will make a bit of sense on these events. The interesting is also that we recognize also the the code number of the malware attack. So if you want to search that specific one, you will get an understanding about what does it mean actually. And there is a detail also based on all the different information. And here we have a look. So it's just a really simple Python. It's just for demo purpose. So here, as I said, I put again the eBPF event. I want to reiterate exactly the same event. We are just importing actually the OpenAI libraries. We are instantiating, we are passing the org ID and the project ID. And if you see here down is where actually I'm mapping together. So I'm passing the PMF data. I'm creating a role. So I want to have prompt engineering. And then at the end, I will query the OpenAI API. And what this will do actually, and it's a really interesting one, I'm also putting exactly what I want to see. So I'm giving an example to make it more as precise as possible the results from the generative AI. And also the results is mapping everything that is finding and making a bit of clarity on the eBPF data, but as well maybe on the attack data. If someone is not familiar with the malware attack or someone is not familiar with the cybersecurity, then it's giving a bit more sense. Thank you so much. I'm giving the word to Michele now.